Hey, VI 101ers. This is Class 12 Evolution 4, Part 3. And you got Dr. Duncan here, and we're going to explore another section of deep time from the Mississippian subperiod to the end of the Paleozoic era. So let's get started. All right, let me get this full screen. Okay. So the Mississippian subperiod lasted from about 359 to 318 million years ago. And we begin to see more events that help shape the landscape of today's Alabama and the Southeast, and of course many other parts of the world. Here you got another picture of the Earth, what it looked like approximately at that time. This would have been about 325 million years ago. In the middle of the Mississippian subperiod. This would be right about here, the location of future Alabama. You'll notice that there's no land there, so we were just seafloor at the time, with covered with shallow tropical oceans. We know tropical because you'll notice that the equator is right here, and our distance from the equator is pretty short. So yeah, we would have been in the tropics about that time. And you can, as you look around on this on the map, you can see the shapes of the different continents here. This is part of Africa. Here's part of Antarctica, India, Australia over here to the right. So what we're looking at here is another supercontinent, not another supercontinent. It's that same supercontinent we saw in our previous explorations of deep time, named Gondwana. And one of the things that was happening during the Mississippian is that Gondwana, the supercontinent, was on a collision course with Laurasia, which is another supercontinent. This Laurasian supercontinent included bits of Scandinavia and North Europe, as well as, if you can recognize this part right here, is North America. Okay, so Gondwana is thrusting its way northward on a collision course to Laurasia. What's going to happen? Well, as those supercontinents start colliding, it starts deforming the shape of Earth's surface and thrusting up some of the seafloor, which then becomes land surface that's out of the water. So here, if you look at the far right, we've got an image illustrating parts of the Southeast. You'll see, for example, the outline of Alabama. I'm tracing it with the laser pointer over here. Outline of Alabama. We see portions of Alabama are now no longer seafloor, but they're actually land masses out of the ocean. Other parts of Alabama are, as indicated by these lighter color blues here, are shallow water ecosystems. So we get a lot of mudstone, as mud was deposited from rivers, like river deltas like this. Mudstone, as well as sands from barrier islands like we have up here. And also coral reefs as well. So lots of shallow water types of environments we know existed at this time in the northern part of Alabama, because we've got rocks that date back to this time period. Sandy barrier islands became sandstone, muddy areas near river deltas became mudstone, and then reefs became limestone, and so forth and so on. Now, Alabama at the time was still south of the equator. This would be the equator right up here in the top left. So if that disorients you a little bit, that's just fine, because remember that the continent of North America has shifted and twisted on its axis over time. And at this point, it's south of the equator and kind of sideways to its current north-south position. One of the types of rocks that formed during this time period is a type of rock called the Fort Payne chert. Now, chert can be formed from a couple different processes, but the type that caused the Fort Payne chert was volcanic ash that erupted from nearby volcanoes. Now, where did those volcanoes come from? Well, they came from this collision zone. As these supercontinents were beginning to crush together, it was deforming the Earth's crust and creating weaknesses where hot molten magma would erupt from deep below, and of course that's a volcano, and then that ash would spew out in the atmosphere and settle out on the landscape. And so we've got out at Ruffner Mountain, if we were to be able to do the hike out there, we would walk through some of this chert and I'd be able to show you this chert and explain that it's came from those volcanic eruptions dating back many, many millions of years ago. Okay, let's take a look over at the far right, and we'll see our geologic timeline. The period that we're covering right now is the Mississippian. Is the Pennsylvanian. We just finished the Mississippian here, and we're now moving into the Pennsylvanian. You'll notice that these are both subperiods that are all part of the Carboniferous period. Now, the Pennsylvanian's also important for Alabama because it was during this time that the two supercontinents, Laurasia and Gondwana, finally sort of ram into each other and form one ginormous supercontinent called Pangaea. And Pangaea was so large that it nearly stretched from the bottom of the Earth, like where the South Pole is today, almost to the North Pole at the top of the Earth. Not quite, but almost reached up there. So this was a massive amount of land. Can you imagine walking all the way through that many different latitudes from the top to the bottom of the planet? Okay, so here we are, here's the future Alabama is like right about here in the center of the screen. We are right there in the collision zone between Pangaea and Gondwana. And of course, that caused the Appalachian Mountains to form. Whenever you get continents colliding, lots of material gets thrust up to the Earth's surface in the formation of mountains. And those mountains were the Appalachians. Now, the Appalachians today are a relatively old mountain chain. They're worn down. They're not very tall in comparison to other mountain chains of the world. But back in the day, back when these mountains were fresh, they were essentially as tall as the Himalayas or the Rockies or the Andes, or all of our tallest mountain ranges of today, which are all relatively young mountain ranges. Okay, so let's zoom in a little bit more on Alabama and what was going on during the Pennsylvanian, because some important things happened here. First of all, take a look at our map. You'll see that Alabama is now mostly out of the water, with just the north central portion of the state underwater. Northwestern corner of the state out of water. And here are the mountains, the Appalachian Mountains, as I just talked about, that are here. Now, whenever you get mountains that are fresh and they're building up, there's going to be a lot of erosion, and that erosion wound up spilling over and towards the ocean to form a coastal plain, much like the coastal plain we have today between here and the northern Gulf Coast. And this was a very low section, lots of streams and creeks influenced by the tides and so forth. We have basically lots of swamps on this part of Alabama's landscape at the time. And these swamps were very similar in many ways to the swamps of today, where there was lots of stagnant water, lots of plants that were growing, lots of animals, of course, as well. Now, the thing that's interesting about this is that these coal swamps lasted for many, many, many millions of years, and allowed a lot of this plant material to build up in the swamp waters. Now, whenever a plant dies, like say out in the forests around here, say here on campus, what happens is that over the next few months to years, that wood material gradually is broken down by microbes and essentially turned into soil. But in cases where plant material falls into stagnant water where there's no oxygen, then that plant material basically gets preserved for long, long periods of time. And the reason being is that microbes, which do a lot of the breakdown of plant material, they're not able to survive in these stagnant waters that don't have much oxygen. And so what can happen is that over long periods of time in swamps, you get the buildup of lots and lots and lots of organic material as plant debris builds up over the ages. What happened in the Pennsylvanian is that this plant material gradually became condensed and compressed, and through some chemical changes became a type of rock known as coal. Now, you probably already know this, but coal can actually be burned. It's used as a fuel. We use it to generate a lot of electricity, and we'll be talking a lot about that later on this semester, because burning of coal creates a lot of problems for us. But to suffice it to say that back in the Pennsylvanian, the formation of all the coal in this part of Alabama and also up through other portions of today's Appalachian Mountains provided us an energy source that we use to this day. In the Birmingham area, we use this and have used this coal in order to melt down that hematite that was developed during the Silurian time period, to melt it down into the more pure form of iron that we use to make pig iron, and then also in order to make steel. Two of the products of Birmingham's heavy industry back in the late 1800s and for much of the 1900s. Now on this slide, I'm just trying to illustrate a little bit about how all the different types of rocks that we find in Alabama made their way to the surface. So if you look up at the top right, what looks like a section of layer cake here, you'll see essentially what happens as sedimentary rock is formed. You get one layer formed, and in this case limestone, and then a flood deposits some sand on top of that, so you get a layer of sandstone develop on top of that, and then some more reef material accumulates, and you get another layer of limestone, and then another layer of sandstone, and so forth and so on. The bottom line is that through sedimentary rock formation, you get these horizontal layers of rock stacked on top of each other. Okay? Now, if you go back to our geology section, you'll remember, you'll look at where we talked about how because sedimentary rock forms in these horizontal layers, anytime you see that rock that is not in horizontal layers, that tells you there's been some distortion to the Earth's crust. So now let's look at what we have here in this second panel down here, and that is to show what was happening to some of Earth's surface as those supercontinents of Gondwana and Laurasia were colliding and forming the Appalachian Mountains. What happened was that as that essentially that layer cake of rock got squeezed from both ends, coming in from the left as well as coming in from the right, that compression from both sides essentially caused the Earth's crust to buckle and to bend like this. And that led to fracturing in some portions that were thrust upwards, like here and here. And then in some places where the forces were projected downward, it sort of squeezed those rocks together and you didn't get the fracturing. Well, what happened over time, over, again, like hundreds of thousands to tens of millions of years, is that these zones that had a lot of fracturing going on, like up here, where you see where I'm squiggling with the marker, that essentially allowed that rock to get broken up and then eroded away. And we see that today in these what are called anticlinal valleys. I'm now at the bottom of the screen. So we got one anticlinal valley to the left, we got another anticlinal valley to the right, and then in some places we get these synclinal valleys. These are the places like up at the top here where the Earth's crust was squeezed together. Not as much erosion happening there because the rock wasn't fragmented. So you might ask, why is this relevant to anything? Well, because of this fracturing, first the folding and then the fracturing and then the erosion of all this different rock material, it essentially exposes many different types of rock at the surface. So if we were walking across this Earth's surface, right where I got the little laser pointer dot walking, we'd see limestone here as we're walking along, and then we crawl up this mountain, up this ridge line, we'd see sandstone, and then here we'd have a sandstone floor of a valley, and then we go up another ridge of sandstone, and on the other side we get into another limestone valley. So instead of just having one type of rock at the surface, like if you look up at the very top where we would just have sandstone, if we had just had no formation of mountains, instead we get two types of rock in this case. We get both the limestone as well as the sandstone exposed at the surface. Now, what does this have to do with biodiversity? Well, sandstone and limestone, they weather into very different types of soils. Sandstone is acidic. Limestone weathers into alkaline or basic soils. and that supports different species of plants, and that supports different species of animals. All that to show how having this topographic diversity in the landscape allows different ecosystems to exist side by side, which supports lots of species, which helps us answer the question why Alabama has so many species. Recall that Mississippi, our next door neighbor that looks essentially like a mirror image of Alabama on the map, doesn't have the Appalachian Mountains, doesn't have different types of rocks exposed at the surface like we do in Alabama. And Alabama can thank the Appalachian Mountains for bringing all those different rock types to the surface. Okay, now we're moving on to the last period in the Paleozoic. We're finally almost done with the Paleozoic, which goes on for quite some time, but had lots of important things to influence Alabama. So here we are over on the far right with our timeline in the Permian. During the Permian, things start to slow down in Alabama. Not as many interesting things happen that we can detect in today's rock records. And that's because Alabama is now completely landlocked and out of the oceans. Because it's out of the ocean, there's no formation of sedimentary rocks anymore. And because there's no sedimentary rocks, we don't have any windows into what Alabama environments were like during that time period. We have to go to other parts of the world to make some inferences about what things would have been like in Alabama. We know one thing for sure, things would have been drier and hotter because we would have been on the interior of the continent at a latitude at about the roughly getting close to today's latitude, where we get into a very dry zone around the planet where we see deserts at about 30 degrees north or so. Also because we were now landlocked and away from the coast and at a higher elevation, no more coal swamps. So those coal swamps that were forming during the Pennsylvanian are all gone now. It's all that coal is locked up in rock at this point in the Permian. And so Alabama stays sort of landlocked and out of the oceans for quite some time. So there's no rocks during the Permian, and that goes all the way through the Triassic and Jurassic. So if you look at the far right over here, you'll see here's the Permian all the way up to the Triassic and Jurassic. This is a big chunk of time for which in Alabama there's no rocks that are formed, or very, very, very few rocks that are formed. Other places are getting plenty of rocks formed, but not Alabama. Now, this is one of the scariest things I think we know from Earth's history. It's the end of the Permian. It's a time of great mass extinctions that occurred. 95% of the organisms that we had from the fossil record up to the end of the Permian, 95% of them disappear completely. They are gone. That is a vast amount of life ending on the planet. It's a time that paleontologists call the Great Dying. And we're not exactly sure what is the cause of this. There are several hypotheses, one of which is depicted in this illustration here, which is there are sections of Asia where there's a lot of volcanic material at the Earth's surface that date back to this time period. I mean, we're talking about very substantial amounts of volcanic material. And that suggests that it was a time period of a lot of volcanism that would have really affected the Earth's atmosphere, causing the atmosphere to become much cooler with all of this aerosol particles accumulating into the atmosphere and blocking sunlight and causing things to cool down. So we would have gone from a very tropical environment to one that was much cooler and harder for species to live, and that could have been the cause for the mass extinction event that happened at the end of the Permian. All of this to say that when there are rapid changes in Earth's climate, it can be very dangerous, very detrimental for existing life forms. Something that we'll be talking about towards the end of this term as we get into understanding climate change and how that's affecting us today. Okay, that ends part 3 of our exploration of deep time. 2 more to go. We're getting there.